Welcome to Speaker Night at the David Dunlap Observatory online with the Royal Astronomical Society of Canada, Toronto Centre. My name is Denise Chilton and I am the RASC Toronto Centre DDO Committee Chair and an operator of the 74-inch telescope at the David Dunlap Observatory. Together with our outreach coordinator, Quentin Wayrich, I'm delighted to be your host for tonight's lecture. I'm also very excited to welcome you, our viewers, to tonight's lecture. If you haven't already, please take a moment to say hi in the YouTube chat and tell us where you are joining us from. This helps us to make sure that our technology is working properly. Royal Astronomical Society of Canada's mission is to enhance understanding of and inspire curiosity about the universe through public outreach, education, and support for astronomical research. In partnership with the City of Richmond Hill, RASC hosts outreach activities at the David Dunlap Observatory, or DDO. The observatory is home to Canada's largest optical telescope. While we miss welcoming guests to the DDO facility, we are happy to bring you virtual programming instead. We would like to start by acknowledging that the David Dunlap Observatory in Richmond Hill stands on the traditional territories of the Wendat, the Haudenosaunee, and the Anishinaabe peoples, whose presence here continues to this day. We would also like to acknowledge this land is at the meeting place of two treaties, the lands of the Mississaugas of the Credit and those of the First Nations of the Williams Treaty. We thank them and other Indigenous peoples for sharing this land with us. It's my great pleasure to introduce our speaker for tonight's lecture, Dr. Elaina Hyde. Dr. Hyde is the director of the Allan I Carswell Observatory at York University. Her research is in and above the cloud, combining astrophysics, data science, cloud computing, planetary sciences, optical engineering, telescope operations, and telescope observations. Her primary astrophysical research focus is galactic archaeology. She has worked with instrumentation and telescopes around the world, and her experience enables her to provide technical leadership for the Allan I Carswell Observatory. Tonight, Dr. Hyde's lecture is titled Telescope Spaceship, an Observatory Journey. If you have questions for our speaker, please post them in the YouTube chat. Elaina will have time to take your questions at the end of her talk. Please join me now in welcoming Dr. Elaina Hyde.
Thank you very much for that wonderful introduction. I hope I live up to it. It is great to be here. And of course, we're going to talk about some of my favorite things, telescopes and spaceships. So what are my favorite kinds of spaceships? Well, they are in fact telescopes. And why is that? Well, I'm going to try to tell you in this talk tonight. So it's a little bit of a fun talk, as you might gather by the first slide here. But I'll just start off with saying, greetings, fellow humans. I hope you will join me tonight on a ongoing mission to observe planets, stars, and even galaxies. And this ongoing mission will be completed through the use of, for tonight's talk, some telescope spaceships over at the Allan I Carswell Observatory at York University. So this is, of course, just one kind of example of what is possible. Of course, at the DDO, I'm sure you have also some wonderful telescope spaceships that we won't be covering tonight, but I'll definitely send some props out to them. So let's go ahead and get started. So first of all, we're going to zoom in, if you will, onto the observatory roof, and we're going to navigate ourselves a little bit through the observatory and into the various mechanisms so that we can start using this spaceship telescope to get out into the universe and to, of course, explore strange new worlds and all of that good stuff. So you'll note here at the top, the first thing you will notice is it is actually two domes, and we'll talk a little bit more about that as we go. But since that has entered our view screen, first thing is to sort of qualify our mission for tonight. And these are the voyages of spaceship telescopes. for this talk. Theoretically, an unlimited mission of exploring all kinds of interesting astronomical phenomenon, not just new worlds, but new stars and new galaxies as well. And of course, any humans that might like to join us will actually have to be practiced in staying up quite late. And as always, trying not to trip in the dark when checking on things in the domes. So, entering into the observatory at York University, we have a little walk bridge that takes us across into the two dome structure. And this is our main observatory. We have two domes for our two largest telescopes. We'll talk about the different telescopes that we have of the just the big ones. The assorted small telescopes are great for things like solar observing and moon observing, but when you want to do astrophotography, having a slightly larger diameter to collect light will definitely help. So these are actually going to be, if you will, our engines of our spaceship, helping us to drive through the stars. So this particular spaceship has two engines or warp nacelles, if you will, and one is carrying a 60 centimeter telescope, and the other is carrying a rather new 1 meter telescope. We do also have a 40 centimeter telescope which has been banished over to the atrium, and other smaller 20 centimeter telescopes, which are, as I said, good for all kinds of things. Those in this case will be sort of our away shuttles. So the 60 centimeter telescope is our oldest and truest workhorse at the observatory. It has been there, I believe, since almost the construction of the observatory in the 60s. The 1 meter telescope is rather new, and it's actually the largest on any university campus in Canada. So, of course, we can't quite beat the DDO, but as far as university campuses go, it's quite nice. So each of these large telescopes inside the dome, the 60 and the 1 meter, are equipped with CCD cameras to image, do all kinds of astronomical imaging. And of course, those will allow us to do the traveling that we need to do to get to all these interesting astronomical effects. So all the telescopes I've told you about, 60 centimeters, 40 centimeters, 1 meter, they're actually named after the size of their primary mirror, just to call that out. Most of you have probably seen telescopes of different sizes. In the case of reflecting telescopes, the primary mirror is telling you what kind of light gathering power the telescope has. So a 1 meter telescope has a primary mirror with a diameter of 1 meter. Most of our telescopes are reflecting telescopes. They're a little bit more compact. They use the mirrors to gather light. And the bigger the mirror, of course, the more light they are gathering up. So this is a very important feature for any kind of telescope. And what we have on the 60 centimeter and the 1 meter are advanced CCD cameras. We also have a special instrument called Quail, which is just going on to the side of the 60, which I'll talk about shortly as well. So this is our spaceship, if you will, and we have our two engines on the side. All right, so let me go through. Here we go. And so if we're going up into the spaceship telescope, we can actually run this pretty much all night. The 60 centimeter has an automated dome, and hopefully this summer, we're going to be getting an automated dome for the 1 meter telescope as well. So we can run them in person or set them up in person and then run them remotely. Very exciting. So, how do we run these spaceships? Well, we have to be able to navigate. And navigation is not as simple as they make it look on the TV shows. So, navigation on telescopes usually works through that telescope having some sort of a drive system. And different telescopes can actually have different kinds of drives. So, if this is your warp engines, so to speak, you want to use these to travel around the sky. We usually use what's called altitude and azimuth or right ascension and declination. Those are basically coordinates in the sky. But to get to that coordinate, you actually have to be able to move the telescope so that it's pointed at the right part of the sky. So what I'm showing here today on the side is the 60 centimeter navigation panel. Now I told you before this was one of our older telescopes. It was made possible to control it with electronic controls several years after it had already been built. And those electronic controls actually read right ascension and declination. So once you've pointed it to the correct spot in the sky for declination, you just have to let it track in right ascension. That's the direction that, of course, the Earth turns, and that's the direction all of the stars will appear to move in. So once you're tracking across the sky, that's actually a little gear sort of tick, tick, ticking on the back of the telescope, controlled by what are called encoders. And so for the 60 centimeter telescope, we have this lovely old fashioned hand paddle where you can actually use the buttons to do the pointing. And it actually does look a little bit like a spaceship. Now, the signal that comes out of here, as shown on the right, this is actually the encoder motor signal, which has to travel all the way over to a computer where you have your sort of computer interface and you can type in it. It doesn't quite look as cool as, a panel of buttons that you can push. Now, the main thing about this control system for navigating around the sky is you do generally need at least one person to help you. You generally have, say, a pair of students, or you're training up a friend to help you run the telescope across the sky. And so these buttons are big and beautiful red, shiny buttons, which are very, very tempting to push. And this is where I usually try to put in a little bit of telescope safety into my observatory talk, because we're going to use this to drive around the sky, see other galaxies, see star clusters, all kinds of things. Make it so, if you will. But we do have to make sure that everyone's trained. So this is my favorite "Can I press the button" picture featuring Quasar and Nili, which are named after astronomical objects. And if you have to ask the question, "Can I press the button?" The answer is probably no, you cannot press the button. So please do be careful with your telescope navigation at all times, especially if it is one of the older telescopes. They do have a tendency to require a lot of extra calibration, or it might even be possible for the gear to go past its motor and run into itself, in which case you would have a warp drive failure because your engine would be down for the night. You would be not be traveling through space anymore. So this is the alignment pad for our 60 centimeter telescope, which is located in our control room. At the moment, we have one control room, which sits in the middle of our sort of two engines, if you will. This is a little bit of the bridge in between the two engine nacelles of the spaceship telescope. And this is where we store all of the processing electronics and computers for the 60 and the 1 meter telescope. And since they both require a little bit of extra, shall I say, coordination with computing skills and that sort of thing, we do have to give them a warm space, because most computers, uninterruptible power systems, cables, power cables actually, and even the extension cords will not react well to temperatures that are far below freezing, which of course our domes do see, because this is Toronto. And as I'm learning, it gets very cold here. So do watch out for that. So fortunately, the control room, or the warm room, as we like to call it, does have all of our various computing equipment, and recently even a mini lounge area. You'll know how small this is if you've ever been in there, but we do actually have a spaceship appropriate captain's lounge chair in the side, which I'm very proud of. So thank you to Dr. Marshall McCall for donating that. We also have, of course, a separate control station for the Quail instrument, which is a brand new wide field camera, which has extremely narrow band filter and just had first light. It's actually strapped to the side of the 60 centimeter telescope, and we'll have a picture to show you that later. But its control system also lives in the warm room for the same reason. So, as with any kind of spaceship, you do actually have to get out there and adjust the controls every night that you want to turn it on. It's really a from cold startup. So, you want to go be able to get in there, uncover the telescopes, check all the gear systems, check that your power is correct. And of course, once you're sure that everything is set up properly, then you can turn on all the buttons and fire up the computers. Don't use any lasers though. So we don't actually have any sort of laser cutters in the telescope. Not recommended. So, pointing out through one of these telescopes at the night sky gives us our spaceship. This is how we travel to things like the moon or Jupiter, which are shown through the open shutter of the 1 meter telescope here. And of course, we're seeing them as they were at some point back in time when the light left their surface and started traveling to us. And so we get a little bit of a time machine as well as a spaceship. And this is why I wanted to call this talk "Telescope Spaceships," because not only are we traveling around through time, we're able to zoom into the solar system. We're able to get into all kinds of different sorts of clusters, able to travel to different galaxies. We do have the time effect as well, and as we go, we get to calibrate our instruments, check our mechanics. So you have basically telescope operators who are the pilots in this scenario. And if they're certified telescope operators, they can also be acting captain. So it's quite fun for all of our crew, especially I think our co-op and high school volunteers have a lot of fun doing this for the first time. And actually, I'm pretty sure the university students have a fun time too. So this is a typical instrument check. This is the 1 meter telescope control I'm going to show you. It is a little bit more modern than the 60 centimeter control, and that's why I've sort of put it up. This is what you might see on the view screen through the computer control on the 1 meter telescope. And what you'll have is some sort of plane wave interface control for moving the telescope, for calibrating the telescope, for focusing the telescope. And then you'll have to turn on one of the cameras. We do have a fancy STXL CCD, but we also have a smaller eyepiece camera, which is located on the other port because it's a dual Nasmyth port telescope. This is really, really handy because it means we can actually permanently mount two cameras at one time and not have to worry about them, remounting or installing them on different nights. So this is the CCD camera, I believe. And this is a image of the moon, zoomed in, of course, as it would be for a smaller field of view. And you can see we absolutely lovely cratering. And there have been some moon mosaics made by members of our crew who I think have made it into the last two observatory calendars, which is really quite nice. Because if you get enough of these and stack them up, it gets to be quite impressive resolution. So just as a little call out, the 1 meter telescope is also a reflecting telescope. It is a newer design, a little bit more compact than the 60, and it does have a much lighter lighter touch in terms of moving it. It's actually a what's called a Dal Kirkham design, and this telescope, it's a corrected Dial-Kirkham, and the design is roughly shown here for those of you who love optical diagrams. So we're playing, now we've gone from playing Captain Kirk to playing Scotty, if you're following the Star Trek references, diving into the engineering of it. What does this engine actually look like? Well, the light has to reflect off of the primary mirror out to the secondary mirror and then through the baffle in the center, where it can either go to port one or port two of the Nasmyth ports. So there's lots and lots of designs for reflecting telescopes. This one is nice and compact, and it basically has three mirrors. You have a concave primary mirror that's 1 meter in diameter, and that's the one that gets its name, a convex secondary mirror, and a tertiary mirror, which is in the middle, of course, directing the light out to one side or the other. So, light from an object, so if we're trying to travel to perhaps your favorite planet, or we'll go to my favorite planet, go to Mars, the light from that object first has to strike the primary mirror, then get reflected up to the secondary mirror, then it's reflected again and goes down through the center of the telescope where it hits the third mirror and then goes either to the eyepiece camera, which is a Malin cam, or to the CCD camera. Each step, which as you reflect the light, of course, we're bringing the light to us rather than physically going to the light. But each step during this process, we are focusing the light and magnifying the object so that we can actually detect it and create an image on our CCD camera. So the dual Nasmyth port is really, really handy. It's in this case, this is a telescope sort of pointed straight out, and that would be sort of north and south or up and down on this diagram. And this port has two, so we actually don't have to switch if we want to go from an eyepiece view to a CCD view. We can just immediately walk out and have it work, which is really, really nice. So very fun. This is much, much easier on the 1 meter telescope than with telescopes with only one port. So our 60 centimeter telescope just had one port at the bottom, and we don't need to detach or reattach any cameras. It's especially the 60 centimeter that requires a ladder and two people. So bring your friends. There are many kinds of ways to mount the telescope. So this is a little bit of a different mount that some of you might have seen before. It's what's called an alt as mount. So it actually moves in altitude up and down, and then in azimuth, which rotates parallel to the ground. Um, I'll try to see if I can find a video of that for you later to show you. It's not the only unique feature. I will mention that it is also very, very silent. So there is something to be said for a newer design using magnets. Our 60 centimeter telescope will use gears to move, which I told you about later, have that encoder signal. This telescope, you would not get that signal from because it actually uses neodymium magnets and coils, which does sound properly futuristic. It's nearly silent when it moves, and it can go very fast. So buyer beware. You do have to watch out that you know where the telescope is and where your head, arms, and legs are, so that you do not accidentally have any kind of collision. This is really cool because the magnets actually mean that the telescope is magnetically levitating. So those of you liking magnetic levitation, again, we have a little bit of uh, a, a, a crossover episode, if you will, just for you. So here's another picture of the telescope in its sort of a more glorious picture, where we're not just showing you the schematic. Now you can see the light that would come in from the open shutter would go down through, and it would hit the primary mirror here at the back. And then, of course, it would go up to the secondary, down through the middle, and out over to the right or the left, which has just been cropped off. And that on the right is the imaging CCD that you saw earlier. And this is this is a really, really fun telescope to move around. It is due to that magnetic levitation, even though it is 1 ton, that's TONNE, that is a very, very heavy telescope. You can actually move it with one hand or even just one finger. I've actually did the test of just seeing if you can put your pinky finger up and give it a push, and you can. So it's a very light to move around, which means that if you are just hopping around the sky, going from object to object, if you wanted to, you could just move it by hand. It also means that we have really, really accurate tracking, and we don't do nightly alignments on this telescope. Um, Something that our 60 centimeter and our 40 centimeter telescope would not like at all. So we now have some details from the engine room here, and the 1 meter telescope being much easier to move does mean that it can do more targets per hour because it takes less time for it to get around the sky. The 1 meter has sensors inbuilt that will read the markings on encoders, which means it can guide itself to the correct position most of the time. It's pretty fun. So basically, all of that is to say that if you want to use this telescope, it's rather easy to get certified on. You just go ahead and turn it on, connect the motors, start the pointing to wherever you want to go, and then your engine room crew will be set for a night of observing. So let me go ahead and see if I could get this loaded up here. All right, so this is a little example taken by one of our work study students just last year. We had them go around and get the telescope in motion. So we did leave the lights on, which you're not supposed to do in the dome. But this is it moving around, and it really doesn't make any noise. If you got a little tiny bit of background noise, that would have been the fans, because it actually has fans stuck in its base that help air circulate around the primary mirror so that it goes to temperature more quickly and actually helps to focus the light a little better. It also helps to dry it out during the high humidity months of the summer, which I am also learning about here in Toronto. So it's pretty fun stuff. All right. So this is a pretty fun telescope, as you can see. This is half of our engine room. We do actually have another half. Let's see here. If I can go here. So this is a panoramic view of the 1 meter telescope, which is showing it a little bit better up against the sky. It is on a raised platform because, of course, it needed to be able to see out of the dome. It's a much smaller telescope in terms of its width than the 60 centimeter, and it's much, much heavier than the telescope that used to be in here, which was only 40 centimeters. And I actually found out just the other day the previous telescope, they actually were able to carry out by taking it down the stairs. That would not work with this telescope because this is so heavy, they had to crane it in pieces through the dome and assemble it on site. So this particular engine was one that is quite a bit more robust. So we have one very, very strong engine and one very interesting and old engine for our spaceship telescope tonight. So we've got, of course, the mandatory robotics discussion. So technically, this telescope is not just a spaceship telescope. It is actually a form of a robot because it does control itself remotely. You can program it. You can program it to have operations. And just in case anyone does find themselves encountered by a robotic telescope, make sure you do know where the emergency stop is. So there is generally always an emergency stop. This is a zoom in of the bottom left-hand corner of our 1 meter telescope, which has a very nice bright emergency stop button, which will just turn off the power and stop it from moving in case you ever get caught out. So this is, always a very important thing. Make sure you know where all your robots are and what they're doing. So our other engine room, as mentioned before, is the 60 centimeter telescope, and this is where I can actually show you engine number two. So our engines are not the same, but it's pretty fun because this telescope is, as I said, the largest sort of weight wise. It's much, much more massive. And I am still not entirely sure how it was constructed with the original building. But it's quite a bit different to move around the sky. It has a massive, massive counterweight, and when it points with RA and deck, not altitude and azimuth like you saw before. But it is also drivable remotely through those encoders in the warm room. And what you see on the bottom, that aluminum hexagonal structure, that is actually quail, which is a wide field, an array, I should say. Forgive me for quail imagers who might be listening to this. It is a wide field imaging array of several cameras, which is actually strapped to the side of the 60. So as the 60 centimeter telescope goes across the sky, it collects light as well through its main port here. The light goes down through to the mirror, primary mirror, back up to the secondary mirror, and then down through the primary again, where it's collected at the back with a CCD camera. Now, that is your main telescope control, but as you're moving across the sky, you are tracking in right ascension and declination if you need to. That means quail, the instrument, can tag along for the ride. So if you really wanted to, you could get quail imaging and 1 meter imaging at the same time. They would be pointed in slightly different directions. This is quite fun, and this is part of a project that is ongoing. They're still not finished building it. I believe we're up to 2 of the 4 cameras, maybe even 3 by now. Very exciting stuff. So this is another view showing the 60 centimeter engine, if you will, or the 60 centimeter telescope. You get a little bit of a better view of quail on the side, and just at the bottom, that is the finder telescope, and you are looking up. So please imagine that you're looking up at the sky right now, because otherwise the angle might not make sense. And on the wall here, you can see that we actually have written reference positions for all of our research objects, SX Phoenicius stars, and that's because this telescope definitely does need to be calibrated. So we have an engine for the 1 meter, we have an engine for the 60 centimeter, and we can drive them around the sky, going to different objects, viewing research objects like SX Phoenicius stars, viewing exoplanets, and getting light from all kinds of different objects. So I thought the Andromeda galaxy would be a fun away mission. This is some astrophotography taken earlier by our own observatory crew at the Allan I Carswell Observatory. This is obviously wide field. I believe it was the 40 centimeter. And with any kind of astrophotography, you're of course viewing that galaxy as it was, when that light first left. So we have a little bit of a time travel effect, as well as being able to visit far, far away places. And for anybody who wants to, who was curious, this is something that they were not even able to do in science fiction, because of course in science fiction there was a barrier around the Milky Way. So with our telescope spaceship, we're able to get to the Andromeda galaxy, the nearest neighbor galaxy to the Milky Way. We're able to travel through our own Milky Way and go to beautiful star-forming nebula like the Orion Nebula. This is a one reduced by observatory member Sana Withers a few years ago, I believe. And this is, M32 or the Orion Nebula. Travel on through bright, beautiful blue stars, lots of lovely gas and dust to explore. And one of my own personal favorites, of course, the planet Mars, which we got to see in opposition not too long ago. So a lot of people in the Toronto area were able to get some pretty good astrophotography of Mars recently. And of course, Mars being a red planet, um, it is not red because it's hot. It is red because of the iron oxide in the rocks of its surface. So we can explore the surface of Mars. We can watch the dust patterns change. We can actually watch for dust storms, which is a fun Mars exercise. And of course, we watch Mars get closer or farther away from Earth depending on our relative distances. So it's very, very fun. We can also take little shuttle missions. So I say we have this wonderful spaceship telescope. We can journey all across the sky. We can actually go to multiple locations at once due to them being able to point in different directions. And we can also take little away missions. And so I thought it would be quite fun to put up one of our smaller Schmidt-Cassegrain telescopes. So some of you might have this telescope if you're a hobbyist. This on the left was one of the original Meade models, I believe, that Leonard Nimoy did an advertisement for. And Leonard Nimoy is the same person who plays Spock in the original series. So that's a little interesting, fun trivia for anyone interested in spaceships and telescopes. Anyways, this one is a little bit older. It's been at the observatory for some time, and we used it to observe the partial solar eclipse, because the partial solar eclipse was very, very low on the horizon. Some of you might remember it was happening just as the sun was rising in Toronto, and that low of an altitude you can't even get to with most big telescopes, certainly not most spaceship telescopes. So maybe you need a little shuttle mission where you drive off and find yourself something that can point to the horizon. So as we're going through all of our missions, we can, sort of beam ourselves up now and talk a little bit about the science. So I think we have enough time for that. If I have not waxed on too eloquently here about spaceships and telescopes, so we want to be able to do science with this observatory, with our spaceship telescopes, and what better kind of science to do than accessible science? So I'll just mention some of our most popular projects. Of course, as you know, my own personal interest is galactic archaeology, but the Allan I Carswell Observatory has done quite a lot of science at different levels for different kinds of folks. We've actually had first year students observing through almost all of the telescopes, the 40 centimeter, the 1 meter, and occasionally even the 60 as well, investigating images of the moon. Looking at the moon never gets old. It's always a treat because as the shadows change, it brings out different features in the craters. And it is really, really fun to try to go through and see how many landing sites and features you can identify. It's also actually quite good for away missions as well. Another fun project of research that we can try to do with this kind of spaceship is we can do galaxy dynamics. So not just the Andromeda galaxy, but anything down to 13th or 14th magnitude is a pretty reasonable target. And we can get imaging in several different filters. Mostly second year students at York get a chance to do this. Actually, their teachers will require them to do it sometimes using the 1 meter telescope now used to be the 60 centimeter, and they'll actually process and reduce that data to determine what kind of galaxy they have. Is it an active galactic nucleus? And actually doing the data reduction is a little bit of work, as some of you may know, but it's really, really fun to get your own reduction and look for specific features. I always like trying to analyze and look for the dust lanes myself. So what other kinds of things can we do? Well, of course, we're not going to talk about all the possible research topics because that would probably take far too long. But another one of my personal favorites is exoplanets. Who doesn't love a good exoplanet transit? And for this, we tend to use the 60 centimeter, although we've started using the 1 meter telescope as well. We take relative photometry. So we take lots and lots and lots of pictures of a star over a night. And of course, we can get data watching as a planet transits in front of a star to look for dips, find the planet's orbital period, size, and density. And that is really, really fun. So if you haven't had a chance to do that, let me know, I suppose, after the talk. Open star clusters are also very, very popular, not just the Pleiades being out there as a bright, beautiful, visible naked eye object, but a lot of fourth year students will often use star clusters to create color magnitude diagrams. The 1 meter telescope and the spectrograph will allow for even more projects, and the spectrograph is technically working. It's just not fully commissioned yet. So watch this, as we say in, at the telescope. Watch this exciting space. It is very fun. So, in terms of research currently running, we have a long term SX Phoenicius star monitoring project, which has been going for many, many years. And we're looking to expand out into my personal area of galactic archaeology as well. So this is a very long-term data set, and I'm not sure that anyone else has this long of a data set quite on our set of stars. We have BE Lin, XX Sig, and many, many others. And this is quite nice because they are variable stars. So again, we can use relative photometry to watch their light levels. All right, so this is a clear night when we just left the dome lights on to get a really good picture. That is the 1 meter pointing out from our spaceship, allowing us to travel off to other galaxies, other stars, other planetary systems. So another fun one, of course, I forgot to mention before, if we're traveling around the entire universe, we probably shouldn't forget to visit, of course, the icy outer solar system. Both Neptune and Uranus are visible. I won't show you any pictures of Pluto through the 1 meter telescope because it looks about as impressive as watching the James Webb Space Telescope. It's a tiny, tiny, tiny dot through our telescope because it is, of course, very, very small. extremely small angular size. But Neptune is really, really lovely. And this is zoomed in a bit. Of course, it's not completely in focus of this image. This was our eyepiece camera with a lucky shot. So those of you who are familiar with Lovecraft, you might have heard of sort of spooky outer space depths and things like that. So the icy outer solar system is always a treat, whether you love watching for Neptune and Uranus or comets or asteroids. Lots of great stuff out there. Lunar viewing, of course, we've already talked about, but I just had to show one more Malin Cam image as a contrast to what you saw before, which was professional sort of CCD images. So we can travel around the solar system just as easily as other galaxies. And I'll just go ahead and do a quick run through for some of our published astrophotography. These are from Sana Withers, who also did some of the previous images. The Crab Nebula M1 is one of my all-time favorites. Stefan's Quintet is a really wonderful group of galaxies, which are actually, you can see in the background here, some of them are truly interacting. And Messier 76, which is one of the most science fiction objects that I have had the pleasure of trying to view. So I think we are about running out of time, if I'm not wrong. So I presume there'll be somebody letting me know from the background whether I was. Um, but it is probably about time to think about finally beaming ourselves up and out. So this is the observatory exit at the Allan I Carswell Observatory, and I thought this would make a good way to to sort of park our spaceship for a moment and hopefully inspire everybody to go outside and look uppity, as they say in well, mostly Australia, but I've started saying it here too. So, just as a conclusion, whether or not you want to view planets or galaxies or just have a fun time navigating around the universe, feel free to make it so and beam yourself up to your local spaceship telescope. And I'll just go ahead and say that you can also, if you have any questions for our observatory in particular, please do feel free to drop us an email at observe@yorku.ca or visit us on social media or, of course, on our website, observatory.info.yorku.ca. So I'll go ahead and say thanks to everybody and thanks very, very much to the DDO for having me here tonight. It's been a really wonderful time.
Thank you so much, Elaina, for taking us along this amazing telescopic journey. We are going to check in now with our RASC DDO Outreach Coordinator, Quentin Way-Rich, who has been monitoring the YouTube chat for questions from our viewers. Quentin, let's start with questions for Elaina.
Hi. So thank you very much for coming on tonight, Dr. Hyde. We do have a few questions from the chat. The first one is, are the new Toronto area LED streetlights easier or harder to filter away than the old yellow streetlights? And
That is an
is from Peter.
excellent question. I am not familiar with the exact optical properties of the new Toronto LED streetlights. I have not. We have actually strongly benefited at the York Observatory, the Allan I Carswell Observatory, because recently the York Athletics Department has put up an inflatable dome over the athletics field, which means that all those super bright game lights are now off, which makes a huge difference. And I'll just say that light pollution is really an issue for so many reasons. It's not just for astronomy, but also for ecology and our local environment. And it's actually very easy to do hooded lights or hooded lamps in your neighborhoods. I mean, substantially harder sometimes to get approval for those. So I don't know if the new ones had the directed light down, but that makes an amazing difference for observatories. If it's an LED light, it would really depend on exactly what luminosity and color the light was.
That's a good answer. I've noticed that new kind of inflatable dome that's been built on the track field. I was wondering if that influence the amount of light coming from the track or not.
Well, in
Another
particular, it was,
question.
yeah,
Sorry.
I was gonna say it was really key because they had lights all around it that they then left off. So that was amazing. Yes, go ahead.
Nice. Yeah. Another question from Peter. How have the number of cloudy nights increased over the years?
Well, I've been in Canada for about 2.5 years. So I'm not the best person to ask, but
Fair enough.
I don't know that it has increased one way or the other in terms of number of cloudy or cloud covered nights. That is I am not sure would be probably the best answer to that.
Okay. I understand from your presentation that neodymium magnets are used to ease its weight to, in effect, make it featherweight to the touch. How does that work?
Well, that's a little bit of a complex question without getting into electricity and magnetism. But the magnetic motors that are called what's direct drive motors, and this is something called a direct drive system. So if you want to read up more on this, you'd want to actually probably check out the plane wave website, and it's actually composed of 24 coils and 32 neodymium magnets, which are powered by something called a phase axial flux torque motor, which is really, really cool. So if you love engineering and magnetic fields, this is great because what it allows you to do is you kind of float above the base. And so that entire telescope that you saw, the 1 meter telescope, has a base that it can rotate around, and that rotation is what allows you to move around. And then the telescope itself, of course, tilts, so you have both altitude and azimuth control. And that rotation is where normally you think, oh, there would be a gear in there. But that's actually where the telescope is kind of floating on this set of pads. And the simplest way, probably the easiest way to understand it, is that magnetic fields interact with things called charges. And if you have two sort of negative charges, they don't want to be near each other a lot. So if you want to make magnetic levitation, just give two things the same charge. It's a bit more complicated than that because of the way that the motors are constructed. It's really, really fun though. So if you want to look it up, three-phase axial flux torque motor.
And I understand that the telescope is actually really quiet when it moves around as well as a result of that. Is that true?
Yes, it is a stealth telescope. So there's a rule at the observatory that if you must always have one other person with you. And if is any person up there where you do not know where they are, you don't move the telescope because it's so quiet. You absolutely will not hear it coming.
Another question. What is the most distant star or galaxy discovered with the 1 meter telescope?
Oh, discovered would be hard. I would have to go and check the record books, and distance is also a little hard because, of course, in space, things at different distances will have different brightnesses based on their luminosity. So a very, very luminous star that's very far away will look dimmer than a nearby star that is less luminous. So when you were talking about how much we can see through a spaceship telescope, well, it's useful to talk about astronomical magnitudes. And higher astronomical magnitudes are larger numbers, which are dimmer objects. And I believe the most faint object that I have seen imaged was 15th magnitude, which is pretty dim.
15th. What is Venus for comparison?
That is a good question. Negative something.
Oh, it's negative. Okay.
Yeah, so Venus.
And
So the magnitude system was built a long time ago, which is why it doesn't make a lot of sense right now. It's so I believe it's a -3 or so off the top of my head. It does obviously vary because as it goes around the sun and we go around the sun, it can be closer or farther away. But the magnitude scale was built a long time ago by somebody who wanted to find the faintest star to the brightest star. And so the brightest star they could see, they called number 1. And then they went to number 9 or 10 or something. Well, maybe 7. But it's not a very good scale. So we regularly have to go into the negative for bright things like Venus or the moon or our own star. So off the top of my head, I think Venus was around -3-ish.
all right. Well, thank you. That's a great answer. I believe that brings us to the end of all of our questions from the audience for tonight. If there are any more questions for you, we will make sure to bring them up before the end of the presentation. Thank you.
Thank you for having me.
Thanks, Quentin, for relaying all of those great questions from our audience. And thank you so much, Dr. Hyde, for answering them in detail. We've learned a lot tonight about telescopes and spaceships.